Following Catherine, Bart Wickl from Stockholm Environmental Institute will join us to discuss freshwater ecosystems and climate adaptation. And finally, but certainly not least, Sarah Leroy from the U of A, University of Arizona, will talk about climate services for climate adapted stream restoration. We hope to have a good discussion at the end too, so please hang on and join us for that. Also want to mention that Catherine had a conflict a little bit later on, so we switched her presentation with Bart's. And also, we're probably going to start, if we can, we may start Catherine's presentation a little bit earlier than 1:35. So hopefully you all can just join us for this entire session and not go in and out, because there's probably be a little bit of an adjustment as we go through. I also want to mention that in the context of this session and the presentations, that we are using the Escalante River as a case study of sorts. The main thrust of this session is how to provide, take advantage of climate services, tools, and strategies for developing long-term viable stream restoration in the context of rapidly changing climate. And so we're using the Escalante River as a little bit of a case study, an anchor to which the other presenters in the panel will refer to from time during their presentations. And we hope to get into climate adaptation, maybe specifically for the Escalante River, a little bit more in the discussion as well. Also, something I want to mention in the context of the presenters for this session is that the majority of them are authors of a recently released guidebook on stream restoration that just came out late last year. The guidebook guides readers through developing a stream restoration program. It's real heavy on lessons learned. Authors come from Australia, Mexico, and the US. You can see the link there. But one of the main reasons for mentioning this is that in chapter 4 of that guidebook, Sarah is the lead author of that chapter. Bart and Catherine, who are also in this session, are co-authors. And Greg Garfin, who presented earlier this morning, are also co-authors of this chapter. And chapters on adapting your stream restoration project to climate change. And I mentioned this in this context, is that a lot of the information that Greg mentioned this morning, as well as what Sarah and Catherine and Bart will mention during this session, is also included or summarized in that chapter. Kind of an FYI. So for the questions and discussion, either at the end of each of the presentations as well as at the end of this session, as we did in the morning session, please type questions in your chat box. Also think, a little bit outside the box, maybe not directly associated with what the presenters are discussing specifically, but what climate adaptation might mean for your watershed, that is the watershed that you live and work in, and how climate information, climate strategies, tools can be used to develop climate adaptive responses in the watershed where you live and work. And if you're a student, we have a lot of students that join us typically for this conference. Please don't hesitate to ask career-related questions to the presenters. This is a great opportunity. The presenters on this panel have many years of experience in natural resource conservation and climate-related fields specifically. So don't hesitate to ask. Think outside the box. We'll end the discussion officially at 3. But if there is critical mass, we can certainly continue a little bit beyond that. But at 3 o'clock, I will, if the discussion is still going, I'll chime in with closing remarks at that point. Okay, Ben and Kara, go ahead and queue up Michael's presentation. And before you hit the start button for his recording, I will go ahead and introduce him by way of reading his bio. All right, so Michael Scott is our next presenter. He's going to discuss the Escalante watershed. After 26 years, Mike retired from the USGS. He retired in 2012. During some of that time and following, he was 10 years as adjunct associate professor at Utah State University. He is currently a faculty affiliate at Colorado State University. Over the past 11 years, has been actively involved in the Escalante River Watershed Partnership and their efforts to restore and conserve riparian and riverine processes along the Escalante River. Some of his recent work in that regard includes long-term studies on long-term cottonwood recruitment in Dinosaur National Monument, Canyonlands National Park, invasion processes associated with the non-native invasive Russian olive along the Escalante, and interpretation of long-term riparian veg change along the Colorado River and Grand Canyon. Thank you again, Michael, for joining us today live, and we'll get to you after your presentation.
Hi there. My name is Mike Scott, and I will be representing the Escalante River Watershed Partnership and Grand Staircase Escalante Partners in discussing the rather extraordinary restoration work that they and their collaborators have spearheaded in the Escalante River watershed. I will present some physical and biological context to this effort, as well as some data related to ongoing and projected climate change within the watershed. I'll then conclude by posing some management questions that we have, including how might we implement climate-adapted restoration within the watershed in the face of future climate warming. Well, this rather hazy turn of the century photo of the Escalante River bottomland shows a broad, marshy floodplain with a narrow, meandering channel and a few scattered cottonwoods on the outer edge of the dry floodplain, or the dry outer edge of the floodplain. Coming out of the Little Ice Age, the valley was filled with sediment, and the floodplain supported a riverine marsh, or a cienega, as these systems are referred to in parts of the southwestern US and Mexico. Soon after this photo was taken, an arroyo cut a deep channel, which then widened and then evacuated much of the valley fill with the riverine marsh along with it, leaving behind a broad, unvegetated channel. As the valley began to fill in the middle of the 20th century, the channel narrowed and the bottomland was transformed to the forested floodplain we see today. These rather dramatic ecological state changes are part of the arroyo cut fill cycle, which are common along streams of the southwestern US. Over the past 6,000 years, the Escalante River has cycled through at least 6 documented arroyo cut fill cycles with accompanying ecosystem changes. And these changes are driven chiefly by shifts in climate. Well, within this broader context of change, a recent and widespread change involving the invasion of the non-native tree Russian olive occurred in rapid fashion along the Escalante River. And within 10 years, watch as the existing cottonwood canopies in this 1999 photo expand, and Russian olive establishes primarily on the moist channel bars and banks along the wetted channel, forming dense bands at the channel edge. Again, this rather dramatic transformation took place within a 10-year period throughout the alluvial reaches of the Escalante River. This invasion altered geomorphic and ecological processes along with aesthetic qualities. Pictured here is a reach of stream showing an example of levee building and extreme channel narrowing produced by Russian olive stems, leaving a channel looking much like an irrigation ditch and leading in turn to channel simplification, along with loss of channel dynamics and critical aquatic habitat diversity. Well, because the Escalante River is set within a landscape of world-class beauty, the invasion of Russian olive prompted the Escalante River Watershed Partnership, Grand Staircase Escalante Partners, and others to initiate a decade-long effort to remove Russian olive, prevent reinvasion, and thus hopefully restore channel and floodplain processes that sustain native riparian vegetation and riverine habitat. This watershed scale treatment and restoration effort was a massive logistical and public relations undertaking, as shown in this illustration by the miles of stream treated within the watershed, indicated in red, both along the main stem Escalante and its tributaries, as well as treatments on private lands within the towns of Escalante and Boulder, Utah. There is evidence suggesting exponential expansion of Russian olive along the Escalante River, as illustrated here as a plot looking at the number of Russian olive stems established in a particular year, was triggered by floods, which then ushered in an extended regional wet period. Though Russian olive was introduced into the towns as plantings of Boulder and Escalante in 1950, exponential growth occurred many years later, around the mid-1970s to 1980, following two large floods, which are indicated by arrows on this graph, following which then was followed by sustained increases in river discharge, as indicated in the graph by the light blue bars, showing the time period of higher discharge. So given the climate sensitivity, the known climate sensitivity of large-scale geomorphic processes and the possible climate connections to plant invasions, ongoing and predicted climate warming and likely drying are concerning to both resource managers and human communities within the Escalante River watershed. To get a better idea of what not only the past looks like, but what the future might hold, we used publicly available downscale temperature and precipitation data to look for any historical trends in both precipitation and temperature. And this figure illustrates the 100-year local annual average temperature, which is the red line, and plotted in each year is the departure of that year's temperature against the long-term average, which extended from 1900 to 2001. And what you can see here is a systematic increase in temperature departures beginning in the mid-1970s, and which are now in the neighborhood of plus 3 degrees Fahrenheit or 1.7 degrees centigrade. In contrast to this local temperature trend. We saw no trend in local precipitation over the same period examined. Now, looking at the future, we used downscaled model projections for the watershed to examine possible future temperature and precipitation. What you can see here in this graph, using an ensemble of 20 models, these models predicted an additional 3 degree Fahrenheit increase in average annual temperature by 2039. Again, we found no significant change in precipitation over the next 20 years. And these projected increases in temperature are predicted both under mitigated CO2 emission conditions or unmitigated or business as usual CO2 emissions. And again, no significant increases projected for precipitation in this future scenario. These observations and predictions on future climate change raise serious and concerning questions on how well conservation objectives and tactics in the Escalante watershed are adapted to projected warmer and drier conditions. Specific questions that we have in this regard include, number one, how are large-scale channel and floodplain processes likely to change, since these processes are critical for sustaining both riparian and riverine ecosystems? Number two, how will non-native plant invasion processes change? Or even more concerning, will they escalate? Number three, with increasing water scarcity, how do we balance human community needs within the watershed against those of water-dependent ecosystems? And finally, leading into this panel discussion, what would a climate-adapted restoration or conservation response on our part look like for the Escalante watershed? Thank you.
Thank you, Michael, for that great presentation. Really appreciate it. Oh, there you are. Good to see you. So we have plenty of time for some questions from the audience. So please type them into the chat box when you think of one. And as we wait for questions from the audience, I got a couple for you, Michael, if you are open and ready, and let other people chime in as we discuss this question. So one thing I was wondering about, Michael, was that with your research on the Escalante, particularly with regard to in the context of Russian olive and climate change forecast, what do you feel how does climate change as it's forecast for the Escalante watershed pertain or will influence, in your opinion, the extent and distribution of Russian olive along the river? And another question too, as you think about that one, is just how would the influence of climate change on the extent of distribution of Russian olive along the river potentially affect either positively or detrimentally the long-term restoration objectives of the Escalante partnership?
Okay, well, with regard to the first part of the question, if there's any possible bright spot for the future, my guess as far as a warmer and drier climate relative to, say, the invasiveness of Russian olive, I would guess that warmer and drier Escalante would perhaps mute the invasiveness of Russian olive, simply because our data showed that once Russian olive dispersed into the Escalante drainage, probably by birds. They established and survived in persistently moist locations on the floodplain. Then matured, started producing seed, which have extended longevity. And then once large floods swept through, dispersed the seeds, the widespread and rather explosive establishment of Russian olive took place. In the future, if the floodplain is hotter and drier, there are probably less sites for these founding Russian olive to establish. So I would guess the invasion process might occur more slowly under a warmer, drier climate. Although I'm guessing there are probably a host of other non-native invasives that would be positively advantaged by that change. So we might be just shifting one restoration challenge to another. As far as now the second question, let me repeat that, make sure I got it. You were saying what are the challenges with the established Russian olive stems along the Escalante? How do they pose a challenge to restoring processes that we'd like to see along the Escalante? Specifically, to me, that would be geomorphically a more active channel that is both eroding, transporting, and depositing sediments, which not only creates a more diverse mosaic of aquatic habitats, it also creates the necessary conditions for establishment and survival of native riparian species. So basically, Russian olive, what it did that first time around in terms of the invasion, it basically locked the channel down pretty tightly and simplified the channel form, again, to look much like that of an irrigation ditch. And there are good reasons why irrigation ditches are not known as hotspots of biodiversity. So to the extent that Russian olive transforms the channel in that way, we're going to lose aquatic diversity and then diminish the opportunities for establishment of native riparian vegetation. So that's the threat.
Cool. Great, Michael. Thank you for that. A couple other questions came in too while you were responding. Eric asked, how is the Escalante projects, how are they being monitored?
That's a good question. Not adequately, in my opinion. And that's not to say that people aren't trying hard to do the right thing. It's just a big task. One of the things that is being done that's very important and is being done well is that people are going in and making sure that Russian olive isn't reestablishing and trying to keep the number of newly established stems down along the corridor. That in itself is a huge task. There's also some short-term monitoring to look at how successful removal has been in terms of restoring more natural channel dynamics. There are also some permanent sort of longer term monitoring plots and transects that are in, but just hasn't been enough time or resources to get on top of that longer term monitoring of permanent transects, say to look at changes in channel width, changes in channel sinuosity and things like that. We've been discussing the possibility of trying to do a larger scale monitoring using remote sensing. And I think that holds real potential, but we just haven't made a lot of progress on that front, primarily because of just time and availability of funds. But But really, I guess my point in terms of the importance of follow-up restoration and follow-up monitoring is that if you spend as much time and effort as been spent and money on restoring the Escalante to the extent that it has been, to me, it's just critical to follow up on and document the effectiveness of the removal in terms of restoring the processes we'd like to see restored.
Mm-hmm. There's another question here, Michael, that's related to what you just said is, are you seeing, maybe based on monitoring, are you seeing increases in channel complexity following Russian olive treatment?
Right. Based on just some fleeting looks here and there at certain locations, yes, there is some response taking place. The channel has avulsed in several places. It's widened. The levees that have accumulated in or that built up in certain places around the Russian olive stems during the initial invasion, those are being eroded during high flows. So yes, I mean there's promising responses, at least in certain locations that we've seen, but we really need to have a more comprehensive, broad scale look at the entire corridor in order to see to what extent these promising changes are occurring on a larger scale.
Thanks for that, Michael. And a couple other questions which kind of more background. Is the Russian olive the main invasive species that the partnership is dealing with, or are there others, particularly with regard to the plant community, riparian plant community?
There certainly it is not the only species. There are a number of other sort of concerning invasive species. It clearly is the most important in terms of its distribution abundance and geomorphic effect on the system. And
have you noticed, or maybe it's caught in some of the monitoring, are natives coming up too? Like
oh yeah,
Salix,
yes,
exiguum,
right. So and one thing I didn't mention is that in the initial treatment process, slash piles were created. In many places, they were left off on the floodplain, but in some cases they were actually emplaced in the channel, which has resulted in some increased erosion and deposition around the slash piles. And in some of those places where we're seeing new deposition of sediments, many of those bars that are being formed are being colonized by early successional native riparian species. So plenty of natives existing in the watershed. So if sort of broad scale channel dynamics increase, undoubtedly the cover of the native riparian species will increase as well. So lots of real exciting potential there.
Cool, that's great to hear. So we're going to jump to Catherine's presentation now. Michael, thank you so much for joining us. Sure. Hopefully you can stay here for the discussion at the end, and we can get more out of you sure. At that point. That'd be great. Thank you again, Michael. Much sure. Appreciated. So moving ahead with to Dr. Catherine Higo's presentation. Catherine is an atmospheric scientist. There she is. Whose research focuses on understanding what climate change means for people in the places where we live. She's a professor at Texas Tech University, has served as lead author on the 2nd, 3rd, and 4th national climate assessments. She also hosts and produces the PBS digital series Global Weirding, and has been named one of Time's 100 most influential people, Fortune's 50 world's greatest leaders, and a UN champion of the earth. Catherine has a bachelor's in physics from the University of Toronto, an MS and PhD of atmospheric science from the University of Illinois. Catherine also gave a great TED Talk in 2018. Go Google that if you if you are interested on communicating climate information to the public. Go ahead, Karen, Ben, with Catherine's presentation.
As a climate scientist, my research focuses on developing the high-resolution projections that people need to incorporate into long-term planning on everything from water management to infrastructure design. Why do we need climate projections today, though? The way I think about it is this. Here in West Texas, we have a lot of very straight roads. They are so straight that you could be driving down them, like this highway from Lubbock to Plainview, Texas. You could be driving down them, staying safely not only in the road, but even in your own lane if you were navigating simply by the rear view mirror. Why is that? Because when the road is straight, then the past provides a reliable guide for the future. But what happens if you're coming up on Plainview here and you hit this giant curve in the road and you are navigating entirely by your rearview mirror? Let's just say you'll end up somewhere you didn't plan to be. And that is a metaphor for how human civilization has been planning over the last decades, centuries, and even millennia. We have had regional variations in climate, and some of those have had serious impacts on local societies and civilizations. But long term, the average temperature of our planet over the course of human civilization has been about as stable as that of the human body until the last century. Today, our collective bus is already veering off the road. Our wheels are on the rumble strip, and that is why it is time to look ahead down the road so that we can all make it around this curve safely together. We know that wherever we live, we have hot and cold, wet and dry. And climate is the long-term average of these weather conditions over at least 20 to 30 years. Over the course of human civilization, again, the long-term average has been stable. But what happens if that average changes? We care about a changing climate because it is altering our average future conditions, and these are conditions that we use for the basis of planning and management. But that's not all. We also see that climate change is altering our variability. And as it alters our variability, it is exacerbating many of the climate and weather extremes that we already see today. We know that across the United States, we see hundreds of these events. Texas has had more than any other state since 1980, but every state has had weather and climate extremes that have caused at least $1 billion worth of damage. These happen naturally. It's as if we have a pair of weather dice, and we always have a chance of rolling a double six. A double six is the heat wave, the heavy rainfall event, the flood, the drought, the wildfire. If you live in Texas, we already have 3 sixes on our dice. But as climate changes, it's sneaking in, so to speak, decade after decade, and taking one and then another of these numbers and turning them into sixes, and even we start to see the occasional 7. And we say, how could this be happening? The answer is climate change. In terms of its impacts on extremes, we see that heat waves are becoming more frequent and more intense, and cold waves less frequent, although we do still have them. Wildfires are burning greater and greater area because it's hotter and drier when they occur. We also see that droughts are getting stronger and longer in many areas of the world, including Texas and the Southwest United States. Heavy precipitation is also getting more intense. Why? Well, warmer air holds more water vapor. And so when a storm comes along, then there's more water vapor for it to sweep up and dump on us. But during droughts, storms don't come along. That's the whole point of a drought. It's a high pressure system or ridge that sits over an area, directing storms away from the area. So the drought gets stronger and more prolonged, and all that water vapor gets evicted out of the area. We also see that tropical storms like hurricanes that get their energy from warm ocean water are getting bigger and stronger, and they have a lot more rainfall associated with them also. So how do we characterize this curve in the road? One way that we can do so is by looking at the past changes that we've already seen. And if we are looking out a few years into the future, up to a decade or so, then the recent changes that we've already experienced are probably still going to be the most reliable guide for that period of time. But again, I'm emphasizing the changes that we've seen, not the long-term average. If we want to look forward into the future, 20, 30, 40, 50 years or more though, that's where we want to start to look at climate scenarios. What are climate scenarios and why do we need them? They are what-if scenarios. What if human population, energy choices, emissions, and temperature changed in a certain way? We need these scenarios because we can't predict human behavior. We humans are the ones driving this change today. All of the warming we are seeing is human-caused and then some. Why? Because according to natural factors, we should be getting cooler right now, not warmer. In fact, it's a little bit like Schrodinger's cat. By looking at the consequences of a higher versus a lower scenario, we actually have some hope that we might be able to change those probabilities. So let me give you some examples. For example, here are the carbon emissions corresponding to a higher and a lower future scenario. One scenario, we continue to depend on fossil fuels. The other, we transition off fossil fuels to clean energy and decrease our energy use through efficiency as well. The way I characterize these two scenarios for the purposes of adaptation planning is like this. The lower scenario represents what we'll have to adapt to no matter what we do, even if we try our hardest. So a lower scenario is a very helpful bench line or base mark of what we have to prepare for. And if a certain system is not able to cope with that amount of change, that's where we have to understand that maybe everything that we're investing might be for naught. But on the other hand, that enormous difference between the two scenarios, that's what can be avoided by prompt action to reduce our carbon and other heat-trapping gas emissions now. And so quantifying the difference between a higher versus a lower future shows us the impetus for why we would want to mitigate, because there might be changes that are too large to adapt to. When it comes to the future, the bottom line is this: the greatest uncertainty is us. So, all right, we know that the future is uncertain due to our choices as humans. We know that we need to use multiple scenarios to capture both the baseline, what we'll have to adapt to no matter what, and also the higher scenarios that show what could be avoided through mitigation. But how do we actually connect this to impacts in the place that we are concerned about? The main tool we use to do that is climate models. Climate models divide the entire world, the atmosphere, the ocean, the land surface, the ice, up into smaller and smaller grid cells. And in each grid cell, using basic physics, they calculate the impact of increasing greenhouse gas emissions or other impacts on climate that can occur naturally on our temperature, our rainfall, and more. This is literally a simple diagram of some of the physics that goes into a climate model. And I don't show you this so that you can peer at the details here. I just show you this to illustrate how complex these models are. What they do, though, is fairly straightforward. They take the initial forcing, which can be natural or due to human activities like carbon dioxide emissions. They take the initial forcing and they look at how that kicks off a chain of feedbacks within the climate system that lead to an even greater warming. That's called climate sensitivity. Climate models, you may be surprised to learn, began a very long time ago. The very first climate model was calculated by hand before we had computers back in the 1890s by a Swedish chemist named Svante Arrhenius. Since then, though, they have evolved very quickly to become some of the most complex pieces of code on the planet. And this diagram from the National Climate Assessment from my chapter 4, which explains scenarios and models, shows how these models are constantly evolving. People often ask, well, I know there's a lot of different models, but can't you just tell me which is the right one? Unfortunately, the answer to that is no. I cannot tell you which one is the right one because there isn't a right one. What we know is that the multi-model ensemble, which means when you put all the models together, the multi-model ensemble is typically closer to reality than any given climate model. And that's not the fault of the climate model. You really have to think of a climate model as a separate planet Earth. It's the same distance from the sun. It gets the same amount of energy from the sun. It has the same layout of continents, but it has a different pattern of natural variability. So let me give you a concrete example so you can see what the output of a climate model looks like. And this is actually downscaled output, which we'll get to in a minute. Here we have annual maximum temperature at one location. This is a weather station in Wilmington, Delaware. The black line is the observed annual temperature from 1960 to 2010, and the colored lines are a bunch of different climate models. So you might say, wow, these climate models are all over the map. How am I supposed to know which one's the best one? Well, again, the point is here, there isn't a best one, but when you put them all together, you see that the long-term trend over climate timescales, and again, climate is the average of weather over at least 20 to 30 years, the long-term trend over climate timescales is nearly identical between the ensemble of climate models and the observations. What's the second thing we see? The second thing we see is that the range of variability is nearly identical between observations and the climate models. So that's why we want to use an ensemble, not to figure out what happened or what will happen on July 18, 2052, but to look at the long-term trend in both average temperatures and extremes over that time. That's what climate models can give us. That's why we should always use climate projections over climate timescales, 20 to 30 years. We should recognize there's no one perfect model. Using as many models as possible is usually the best way to go. And we have to realize that there's no scenario that's more accurate because scenarios are driven by human activities. So we have to look at the future as sort of an if-then. If we do this, then this is what is going to happen. And lastly, we have to recall that because we're conducting a truly unprecedented experiment with the only planet we have, there is always the chance of surprise. So it's better to be safe than sorry. What does climate model output look like? Well, for the United States, we see up at the top the observed trend in temperature over the last century. And then on the left-hand side, we see the projected change under a lower scenario. And on the right-hand side, we see the projected change under a higher scenario. This illustrates the impact of our choices. But global climate model output at the scale of the entire United States, it can tell us that there is a trend, it can tell us the direction of the trend, and it can even often tell us a little bit about the magnitude of the trend, especially in terms of average temperature and average rainfall. But often we need a lot more than that. We want highly granular, detailed information for the places that we are concerned about. So that's where downscaling comes in. What is downscaling? Well, you have the different global scenarios that go into the global model, and then it produces information at the scale of the global model, which is typically 100 to 100 miles per side, per grid cell. And then we can downscale it to either individual weather stations or to a fine scale grid. There are many different approaches to downscaling, which is best depends on your resources and on your needs. So for example, if you're looking at a watershed that's fairly large, so a gridded data set of downscale projections at 1/16th degree, for example, would give you adequate coverage and resolution over the watershed. And if the topography doesn't vary too much, then a gridded data set might be perfect. On the other hand, if you are looking at a watershed where the topography varies significantly over very small spatial scales, or maybe you already use specific weather stations or gauges that your model is built off of, in that case, individual weather station projections might be more useful. And these are just two pictures here contrasting the two different approaches. So whether you use a grid or weather station information, again, depends on what you're most used to using. There's also two different approaches to downscaling. You can do high-resolution regional climate model downscaling, which gives you a grid, or you can do empirical statistical downscaling, which will give you either a grid or weather station output, depending on what observations are used to downscale. Each of these approaches has their uses. Each of them has their benefits and drawbacks. So statistical models are computationally efficient. They can run lots of different global climate models, lots of different scenarios, and they automatically bias correct the global climate model output so it's ready to be used. Regional climate models, though, have all the dynamics in them at the high resolution. So they can simulate, for example, the effects of topography on climate at a much finer scale than the GCM. They can also generate output for a lot more variables. Statistical models typically just do temperature and precipitation. Some of them can do solar radiation and humidity, but regional climate models can do a whole suite of variables with different soil layers and different layers in the atmosphere as well. You can also use regional climate models where you don't have any observations, but statistical models are limited to where you do have observations because that's what's used to train the model. So if I were working in a region with few or no observations, or if I needed a large suite of complex variables like cloudiness, soil moisture, solar radiation, wind, I would use a regional climate model. On the other hand, if I were working in a region that had observations and I wanted projections that actually matched the temporal and spatial scale of the observations that I was using, or if I wanted to make sure that I had lots of different global climate model inputs and multiple scenarios, then I would go for a statistical model. What does this look like? I want to just give you an example here. This is a map showing where we have downscaled weather stations in Ohio, as an example. These are all weather stations. And across the US, we've downscaled temperature projections to a lot of different weather stations. And this animation shows, I think, 200 of them across the US. And what we've done is we've calculated the temperature of the hottest day of the year moving forward into the future, starting in the 1950s and going through to the 2090s. You can see how the temperature of the hottest day of the year increases over time under the higher scenario. So this brings us to our third and last question. How do we know what we need? Well, the first place to start is not with me, it's with you. What impacts do you care about? Do you care about drought, about heavy precipitation, about water shortages? What do you care about? And then step number 2, how do they connect to climate? So start with what matters to you in terms of planning and management, and then say, well, how does that connect to climate or weather? And then step 3, we can say, all right, how are these things changing? In some cases, all you might need to know is the fact that they're changing in the direction of the trend, because whatever management options you have available to you are not going to change significantly if I told you that heavy precipitation is getting 2 times more frequent or 3 times more frequent. If you would do the same thing anyways, all you need to know is that it's getting more frequent. And this type of information can be provided by regional assessments and by national assessments like the U.S. National Climate Assessment. Other times, though, you need more information. You actually need to have quantitative information that tells you the range that you can expect. So for example, if you knew that heavy precipitation was going to increase somewhere between 3 to 5 times, and the 3 was at the lower end of the scenarios and the 5 was at the higher end of the scenarios, so you'd have to adapt to 3 no matter what. But if you wanted to be safe rather than sorry, you might want to adapt to 5 times. Then that's where quantitative information can help. If your response is going to differ depending on how much things are changing, that's where you need quantitative information. And in the guidebook, we have a lot of details, and in Sarah's presentation coming up next, there's a lot of details about how and where you can find that quantitative information if you need it. But again, a lot of times you might start off thinking you need it, but it turns out that your adaptation options are so limited or prescribed that all you need to know is how things are changing and in what direction, and that gives you the information that you need to act. The bottom line is this. The future is uncertain, but we do know enough to act now. Our collective wheels are already on the rumble strip. The curve is looming immediately ahead, and it's time to take our eyes off the rearview mirror, maybe just keep one eye on it, and the other eye ahead down the road, because our goal is the same. We need to plan for that curve in the road to ensure that we all make it around safely.
Thank you, Catherine. That was excellent. Right on the money. That was a fantastic presentation. Are you with us?
Yeah, I'm right here.
Excellent. Well, thank you, Catherine. Again, that was fantastic. And a shout out to our audience. Please remember to include your questions in the chat box. And while we wait for the questions to come rolling in, before I ask mine, Catherine, how much time do you have?
I have till the hour.
You tell the hour. Okay, great.
And then I'm going to come back after Sarah's presentation, hopefully to join the panel.
Oh, fantastic.
Mm-hmm.
Excellent. Great to hear. The question I have is, for someone like who's working, say, a practitioner, say, for example, in the Escalante, that's kind of our case study that we're using here in this session, who's funded modestly. And as you pointed out, they probably have a good idea about what they want to know with regard to climate change. And they want to figure out, okay, is the system drying? What are the chances of high, frequency of high magnitude floods and that kind of thing. But just maybe this is more of kind of a process communication question is, what would you advise as sort of the practical steps for somebody to kind of begin to communicate to the climate world and get their head around some of the models and what that might mean for their restoration program?
Yes. So as I alluded to in my presentation, often we think, oh, well, we want to implement climate adaptation, so let's go out and find the climate information we need. But really, we have to flip that. We have to ask ourselves, what could we do? Because in some cases, when we start to look at options of what we could actually do, and it's helpful there to have trends, so you at least know, is heavy rain going up or down or temperature going up or down. But what can we do is the most important question, because sometimes you might go out and spend your limited resources getting the most detailed information that you can, and then you bring it home and you realize, well, it's our end result, our end decision is no different than if somebody just told us, hey, evaporation is increasing, heavy precipitation is increasing, and temperature is increasing. And we would have done the same thing anyways. So in a way, I almost want to work myself out of a job, so to speak, by saying that you don't necessarily have to go as detailed and sophisticated immediately as you might think. First of all, ask what you can do. Then if you want to know about sources, I'm really excited that we have another brand new book coming out. So obviously Renewing Our Rivers is a book specifically aimed at streamflow ecology, or streamflow hydrology. But I also wrote a book with several of my climate science colleagues that is aimed not at climate scientists, but at people who are looking for climate information. And it's called High Resolution Climate Projections. And it's coming out from Cambridge University Press. I think it should be coming out any moment now. So I'm just going to find a link to that and put it in the chat. And so if you want the Cliff's Notes version, Renewing Our Rivers has that. If you want to do a deeper dive, this book has it. But before you do anything more than what we have in Renewing Our Rivers, I would say ask yourself what you can do first.
That's great, Catherine. And I just wanted to mention too, that you had a lot of accolades coming in the chat room saying how great your presentation was. So I just wanted to make sure you saw those. Let's see. And then the question is, that came in from Rachel is, what can we do? She said, I love that you said that, and so important that we are trying to work on the ground with private landowners often. And I don't know if you want to comment on that comment. I guess there really wasn't a question associated with that.
Sure. Well, so I just put the link to the book I alluded to that does a deeper dive there.
Excellent.
And then in answer to Rachel's question, I'm actually going to put a link to my TED Talk.
Yeah, it sounds like it.
Yeah, because if you survey people across the US, 2/3 of people across the US don't hear anybody else talking about climate change, let alone have a conversation themselves. And if they never talk about it, why would they know why it matters? And so simply talking about it is one of the most important things we can do, saying, and talking about it from the perspective of, I'm worried about this, and I bet you're worried about this too. So I'm worried about what this is going to be doing to our flows. I'm worried about what it's going to be doing to a specific species or to the viability of the ecosystems on your land. I'm worried about what this would mean for even just the character of the place that you know and you love. And so really sharing from that perspective, not assuming that the other person you're talking to is going to be in opposition to you, but assuming that you're working from a place of shared values. It's so important. Oh, Lisa has a good question. And I love that you're continuing the metaphor of the road there. That's great. How do you keep the car on the road? Well, strangely enough, for adaptation, you don't even have to have everybody on board with the idea that climate is changing due to human activities. In fact, I've had very productive and successful interactions with people here in Texas, like water managers and producers and people who own land, where they're not willing to say it's humans, because that's actually a political trigger for many people, but they are willing to say something's different, something's getting weirder. This is not the way it was back when they were young or back when their father owned the land or their grandparents owned the land. So people are willing to say that something's different. And if you have a plan, so they're willing to say there's a curve. They're not willing to say humans made the curve, but they're willing to say there's a curve. And often I find using data that they're familiar with for the places where they live helps to kind of solidify the fact that the curve is there and it might even be bigger than they thought. And then constructive, positive solutions to get people on board together to make it around the curve really make a big difference. Because nobody wants to know there's a problem, but there's nothing they can do to fix it.
Catherine, we are just about on the hour, about 1 more minute left. So I know that you're squeezed for time right after this. So maybe we'll leave it there for now. And then if you can join us for the discussion later on, that'd be fantastic.
Yes. Thank you for having me. And the next couple of presentations are going to be fantastic because they will dig a lot deeper into why is adaptation needed. And then once you're on that curve, how do you find the information that you need to characterize the curve? So stay tuned because we have not left this topic. This whole session is about this.
This whole session's on it. Thank you again, Catherine. Greatly appreciate it. See you soon. Okay, our next presentation is by Bart Wickl. And Bart Wickl is a senior scientist, conservation hydrologist with the Stockholm Environmental Institute, which is based in Davis, California. Bart's work focuses on spatial analysis, tool development for sustainable water resource, freshwater ecosystem conservation in a changing climate. He has worked on a broad range of development contexts, river basins around the world, focusing on conservation and water resource development, remote sensing and GIS, spatial analysis, climate change, adaptation, land use and hydropower, development impacts, and ecosystem services. Bart has done it all. Prior to working for the Stockholm Environmental Institute, he was a lead hydrologist with WWF, World Wildlife Fund, Conservation Science Program, and holds degrees from the University of Amsterdam and University of Bonn. Go ahead and cue up Bart's presentation, Ben.
I'm a conservation hydrologist with the Stockholm Environment Institute in Davis, California. This talk was prepared for the RiversEdge West Annual Conference and aims to provide a perspective on climate-adaptive approaches to river restoration under a rapidly changing climate. When talking about climate change, you may have heard the terms mitigation and adaptation. Mitigation aims to slow and eventually stop our post-industrial level emissions of greenhouse gases. And if mitigation works, we will reduce the rate of climate change within the next decades to 100 years. Adaptation is the process of adjusting to and preparing for the impacts of climate change, while we are bringing our emissions down. If adaptation works, we will start reducing our vulnerability to impacts today. It's important to recognize that adaptation without mitigation is not possible. Climate adaptation aims to minimize the risks associated with man-made climate change and primarily focuses on building and maintaining resilience. Adaptation can be seen as buying time while we stabilize and reduce our emissions. People and nature have been adapting to changing climate conditions for millennia and beyond. So some will say, what's different? Well, the current rate of change that we're experiencing today is much more extreme and faster than we've observed in the past hundreds to thousands of years. In addition, it's very important to acknowledge that, especially in the past century, the world has also dramatically changed, resulting in the loss of habitat, connectivity, species, and we've over-allocated water resources. And therewith, we've dramatically reduced the ability to adapt. As pointed out by Millie in 2008, many of our approaches to water management are founded on an assumption of stationarity. When we designed our water management infrastructure, such as dams, irrigation districts, flood control structures, we have generally used observations of the past to prepare for future conditions. This has resulted in the fact that many of our policies, institutions, and infrastructure design and conservation approaches are fundamentally flawed in their ability to adjust to emerging conditions. One of the most common examples is the exposure of coastal communities. Approximately 40% of the global population lives within an area with rising sea levels. While countries like the Netherlands, where I'm from, have shown that it's possible to adjust to these conditions, it needs to be acknowledged that there are hard limits in our ability to engineer ourselves out of these problems, primarily due to costs, but also technical limitations. A great example of a piece of infrastructure that was designed with a mismatched hydrologic reality is the Hoover Dam. As some of you may know, the Hoover Dam was engineered based on approximately 30 years of hydrologic observations, which in retrospect turned out to be the wettest decades in Colorado River Basin history. Once such a piece of infrastructure is in our landscape, we have significantly reduced our ability to adjust to other conditions. And both from an engineering and environmental perspective, you end up with a maladapted situation. When we look at the past 100 years of change in, for example, temperature in the top left map, we see a clear pattern of strong warming and some moderate areas of cooling around the globe. For precipitation, however, the top right map, this average signal is nowhere near as consistent and much less predictable. The same goes for projections based on state-of-the-art climate models, which indicate a strong consistency in trajectory towards continued global warming, as represented in the figure on the bottom left. For precipitation, however, there's a broad scattering of projections and no consistent global or regional direction for emerging patterns and conditions. When discussing climate change, there's a strong emphasis on global warming, changes in temperature. A lot of the changes that we may experience or are experiencing already actually come to us through changes in the hydrological balance. We get more extreme events such as floods and hurricanes. There are shifts in seasonal onsets of spring burst, changes in snow and ice melt, and the duration of dry seasons. And we are already experiencing system level shifts in fire regimes and systems moving from perennial to intermittent flows. When we discuss climate change, change is often presented as a change in average global conditions. By 2050, for example, we'll have a 2-degree increase. But the reality is that the changes in our climate come to us in a variety of changes. We have changes in extreme events. We have shifts in seasonal and annual dynamics. And we can even have state level or system level shifts. And so when we're designing our climate adaptation options and are evaluating the impacts of climate change on our conservation efforts, it can be helpful to conceptualize the different kinds of changes that might take place and how they affect our objectives. In extreme events, we expect both the intensity and duration of events to increase and the return periods to shorten. We already see this with the fire regimes, for example, in California, where the return period has dramatically shortened and fires have become much more extreme. Seasonal shifts are reported widely throughout the world. In the Northern Hemisphere and especially in the United States, we already see shifts in onsets of spring, earlier springs. We see stronger, deeper polar vortices and longer dry periods and a greater frequency of heat waves. In some parts of the country, we see shifts. For example, in California on the West Coast, we see fire-adapted forests shift towards grass-dominated ecosystems, resulting in Arizonification of our ecosystems here. In places like Oregon and Germany, wine industries are booming, while southern industries are struggling. To a cascade of impacts due to changing flow regimes, which in turn affect sediment balances, and eventually habitat structures. When we are designing river ecosystem conservation strategies, it's therefore logical to evaluate this interdependency. This cascade of impacts is what's already being observed in terms of geomorphologic change, for example, in the Escalante river system, as shown by Mike Scott in the previous presentation. A qualitative approach towards adaptation is a thought framework that lets planners, decision makers, and practitioners evaluate the broad range of uncertainty that is inherent in natural science and climate-related work. One could, through a set of guided questions, evaluate the state of our current knowledge, but also evaluate less likely events and how one would potentially prepare for those, and possibly design low-risk pathways that aim to embrace uncertainty rather than ignore it. Adaptation in many cases may end up resulting in very similar actions to the ones that we're employing now, but the most important difference is that we're deliberately exploring the potential impacts of climate change and are monitoring for the indications of change that help us adjust our actions more dynamically. When designing climate adaptive conservation strategies, we can employ a variety of qualitative approaches. When preparing for extreme events, one can consider historic events and evaluate where our responses failed in the past. And consequently, we could aim to do better. Some climate disturbance events related to, for example, El Niño, are more predictable and can be used as a proxy when thinking about adaptation strategies. Imagine, for example, what happened during the last El Niño events and prepare for those events to be more frequent and more intense, and think about how we would change our strategies based on that knowledge. In the context of Rio Grande Basin conservation, we started integrating climate proxies, which means we were looking at places, for example in northern Mexico, as a proxy for future conditions in Texas. Through temporal proxies, as a way to develop climate adaptation, we looked at recent severe droughts as a means to understanding how future drier, warmer conditions might affect natural processes in the watersheds that we work. Understanding tipping points is arguably one of the most important aspects in climate adaptation, which allows us to determine both the direction of change and a potential point at which certain strategies don't make sense anymore. Rather than pushing a boulder back uphill, we could find ways to facilitate change and adjust accordingly. Lastly, monitoring is becoming increasingly important to understand the changes taking place and to evaluate the effectiveness of our chosen approaches. The case of the restoration of silvery minnow in the Rio Grande provides some surprising ideas for potential adaptation strategies. Silvery minnow has experienced a dramatic reduction in its original range due to damming and over-extraction of water for agriculture and industry over the past decades. The species has been experiencing increasing climate pressures over the past decades as well, through longer low flow conditions and changes in water quality. For many years, Fish and Wildlife agencies have attempted to release and reintroduce silvery minnows in the Rio Grande, often causing conflict with farmers. A few years ago, biologists discovered that one of the reasons that the reintroduced minnows are surviving dry periods turns out to be the fact that they can enter irrigation canals through screens, while larger predatory fish are screened out. Deeper ponds in the irrigation system allow the fish to survive and come back once the river flows are back up. So with these surprising new kinds of refugia, we may be able to design and engineer better solutions for these fish than we are doing right now. This also shows that there might be synergistic benefits, and sometimes small modifications in management practices may have big impacts. So looking at adaptation measures in this kind of context, what would they look like? Well, we could map refugia and put stronger emphasis on the conservation of refugia, springs and seeps, along with adjustments in flow management. We should, however, also explore at which point we may have to give up on conserving this kind of species. The case of the Escalante River, shown in the previous presentation by Michael Scott, is facing challenges with the expansion of invasive Russian olive. Current efforts focus on eradication and the planting of native species. Adaptive strategies in this context might emphasize the importance of tipping points and understanding when we won't be able to go back to a system without the presence of this invasive species. We could also explore synergies in adaptation efforts by focusing on restoration of reaches that would benefit fish species as well as other conservation targets. When approaching eradication efforts, we could imagine taking a general upstream-downstream connectivity into account and design an approach that would work from the headwaters towards the outlet to prevent reseeding and managing flows to prevent kinds of events that trigger the recruitment of new reaches by Russian olive. While this is by no means a comprehensive review of all aspects of climate adaptation, I hope that this brief overview provided some guiding adaptation principles and help you in designing future adaptation projects. The role of tipping points in the exploration of novel and sometimes unusual synergies might be more important than is currently thought and could help identify climate change as a new opportunity for collaboration rather than an area of conflict. Thank you for your attention.
Bart, thank you for your presentation. A lot of great information in there. Are you with us, Bart?
Yeah, can you hear me?
Yeah. Thanks.
Okay, yeah, I can't seem to make the camera work, but the microphone is working. I don't know what's going on there.
Well, we can't see.
Apologies for that.
That's all right. See your smiling face.
Yeah, you're not missing much.
So a reminder to the audience again, please type in some questions for Bart in the chat room. I don't believe I have received any yet. And while you're doing that, Bart, I have a question for you from my experiences and working with you actually at with WWF. Was one of the big objectives that always comes up with regard to developing a climate adaptive project is changing water management. And that is where, at least with my projects, we've always run into a huge, it's a real uphill climb, so to speak. And I was wondering, it's just like, maybe you can just, if you have experience with that, do you have examples of work that you've done where water management has been improved based on climate change predictions? I'm thinking in particular water management associated with impounded rivers. But any insights on that and what in the process, what was done and how you communicated with water managers if that was successful?
Yeah, absolutely. Well, yeah. The challenge with environmental water and e-flows as a field, environmental flows is typically an area of conflict, right? You over-allocate water that now you're trying to get back towards the environment, and that's challenging, especially places like California, Texas, Mexico, where we've worked together We found some hopeful examples in Mexico, though, where through a national environmental flows program, we were able to convince the National Water Agency that it actually was in their interest to implement a water reserves program and use climate change as a motivator to be more cautious in the allocation and over allocation of water, to prevent over allocation. Now, that worked well because through that approach, we worked primarily on basins that still had a greater degree of availability of water. But we managed to convince them that preemptively allocating water for the environment and recognizing the environment as a legitimate water user was a very good idea. So that I'd say is one example. That doesn't take away that it's complex to work in these over-allocated basins. I think there are some examples in the US, California, where we are making headway in bringing water managers and environmental users or groups together, primarily through better knowledge about how a system works and when water is needed. So part of it is not just the over allocation of water, but not having water at the right moment in time. And sometimes smaller modifications may have great impacts. So I think that's another area of success and potential for further exploration.
Thanks, Bart. As a follow-up to that, one of the things that I've been thinking about too, with regard to water management in the context of climate change, is that there seems like, from working around Mexico and the Southwest US, there are examples, but they're small scale. Like, for example, improved water management in an irrigation district, so that the water that's being managed in the reach of the river that passes through the irrigation district is improved for the benefit of both the farmers and the species, the native species that rely on that stretch. But it's really small, right? It's just through that particular irrigation district. And I've always wanted to, kind of a magic wand kind of thing, if I had some grant funding or something, is to visit some of these areas that have done these kind of progressive water management reactions in the context of climate change, and just kind of do a kind of a lessons learned, how could it be expanded type of project. And I just wanted to ask you if you see the same need, maybe with your work in California and other countries, in other parts of the world, and also if you have come across any kind of documentations that would expand on lessons learned from such projects.
Yeah, again, it's a bit of a challenge. In the US, we have depending on what size measure you employ, over 75,000 dams and pieces of infrastructure in rivers. So we've heavily altered the plumbing. In my work, I've been focusing a lot on relatively unaltered basins, and I think the opportunity there is to bring that message from this experience from the north, from Europe and from the US, to those places where you haven't fully altered the river basin yet, and also point out the fundamental vulnerability of these large infrastructure projects themselves to climate change. Another point of hope that I identified is, while there is a lot of climate skepticism, as Catherine pointed out, people who really are affected by these changes care and are worried. And you see investors, hedge funds, companies that rely on water for their bottom line, drink companies, beer companies, they all are worried about climate change. And so there is also a great opportunity to look for solutions. And you see that environmental scientists have a lot of knowledge at hand and a lot to offer in those conversations. So I also like to see climate change as a conversation starter and to have a joint, an unusual combination of interests. Let's put it that way.
We should write a proposal together.
Yes.
There's a question from Lisa. Do you think the prior appropriation system needs to be revised to allow leaving water in the streams for restoration purposes?
Oh, yeah. Well, there you go. No better example than California.
Yeah, right.
Take water out of people's hands. It's it's really hard. But yes, I think that there's a need to really rethink much more broadly how water has been appropriated or allocated, and how we can transition to a new water management reality. And in a way, maybe there's a bit of similarity between the lock into fossil fuels and everybody just having this already deep dependence on fossil fuels, and now being told, well, we need to transition to a completely new kind of economy and world with renewable energies. And that's maybe equally hard, but people are starting to do it because it is in their own interest, and there are, of course, also mechanisms in place to facilitate that change. I think similar things need to happen with water management.
Yeah, exactly. And one last question, or really a kind of a comment from Ashley here, Bart. She says that there should be a lessons learned support group that hosts each other to review lessons learned from innovative projects, kind of touching on a little bit what we were discussing before. And couldn't agree more with that.
I think the anecdotal examples that were thrown out there, there's many more where those came from, and I think through proxies, through other experiences, and exchanging those experiences, we can learn a lot. I think California can learn a bit, for example, from the example this morning of how Colorado is starting to manage or connect water management and land management, forest management.
Right.
Evaluating forest to higher impact. So, there's a lot of opportunity there.
Well, Bart, thank you. We're going to move on to Sarah's presentation now, but greatly appreciate you joining us, and hopefully you're sticking around for the discussion.
Yes,
part at the end. Okay,
absolutely. Yeah.
Thank you so much, Bart. So moving on to Sarah Leroy's presentation. Sarah is an assistant staff scientist with the Arizona Institute for Resilient Environment and Societies at the the University of Arizona, and the Science Communications Coordinator with the Southwest Climate Adaptation Science Center, which is a partnership between the USGS and a consortium of research institutions in the Southwestern US. Sarah works to bridge the gap between science and society, and works closely with decision makers to get them specific science information they need to make management decisions. Go ahead, Ben and Karen, with Sarah's presentation.
Good afternoon. I recognize that I'm recording this ahead of time, but assuming that everything has gone to plan today, we've heard some amazing talks. My colleagues have showed us how climate change is impacting the Southwest US and what projections are showing us for the future, as well as how sensitive Colorado River runoff is to warming. They've discussed climate adaptation strategies and freshwater ecosystems, and how we can use climate projections and other data and tools to aid in resilience planning. And we've also learned about a specific case study on the Escalante River watershed. And so I'm going to attempt to bring it all home with next steps and specifics for how stream practitioners can find climate data and information to assist in developing an effective climate adapted response. So first, I'd like to acknowledge that the information I'll be presenting mostly comes from this recently published guidebook, which has likely already been mentioned today. The book is about designing and implementing stream restoration in the Southwest US, Northern Mexico, and Australia, and it includes chapters ranging from planning and implementing your stream restoration project to all the way to monitoring. I was involved in the chapter on adapting your stream restoration project to climate change, along with the other authors that you see listed here. One section of this chapter is dedicated to highlighting and describing sources of climate data, predictions, and climate projections that stream practitioners can use to adapt their restoration project to climate change. And these sources of information are what I'll be highlighting today. So climate services is an umbrella term that really refers to any group that is involved in gathering, analyzing, and distributing climatic data, projections, or information to the public. Data they tend to provide to end users can include weather station data, seasonal predictions, and long-term climate projections. And they can also help restoration teams in a variety of ways, including assisting with, including assisting with the collection, analysis, and interpretation of climate data and securing additional resources to address gaps in knowledge. And in the past decade or so, the number of climate service providers has really skyrocketed. So in the US, for example, some examples include the National Oceanic and Atmospheric Administration, the Regional Integrated Sciences and Assessments Program. So those are referred to as the NOAA RISAs. The USDA Climate Hubs, the National Integrated Drought Information System, or NIDIS, the Regional Climate Centers, and the USGS Climate Adaptation Science Centers, or CASCs, of which I am a part. In Mexico, the Mexican Institute of Water Technology and the National Institute of Ecology and Climate Change can be considered climate service providers. And each provider fills a unique niche, and they tend to work closely together to leverage each other's strengths. So the Climate Adaptation Science Centers are a good example of a climate service provider. They work mostly with natural and cultural resource managers and are focused on co-produced research, or research that is conducted with managers to ensure that their research results in tools, techniques, models, and actionable information to facilitate robust decision-making by resource managers. And so there are 8. We just added a Midwest center, so my apologies. There are 9 centers across the country, and all are under the Department of the Interior and managed by the USGS National Climate Adaptation Science Center. They provide funding opportunities, trainings, and workshops for natural resource managers and researchers in the region, as well as dissemination of relevant research through webinars, podcasts, fact sheets, and other outreach materials. So I am the Science Communications Coordinator for the Southwest CASC, which is one of these regional centers. Like the other centers, we are a collaborative federal university partnership between the USGS and 7 academic institutions from across the US Southwest. So you can see in the orange map there. So the mission of the Southwest CASC is to work with natural and cultural resource managers to develop and deliver scientific information and techniques to anticipate, monitor, and adapt to climate change in the southwestern United States. So another climate service provider that fills a different niche are the USDA Climate Hubs. While the CASCs mostly work with natural resource managers, the Climate Hubs were established to deliver science-based knowledge, practical information, and program support to farmers, ranchers, and forest landowners. So a different group of stakeholders. And in partnership with various entities such as universities and farm groups, they provide tools, strategies, management options, and technical support to help land managers adapt to climate change. So in our region, the Southwest Hub, the Southern Plains Hub, and the California Hub, they all serve the US-Mexico border region. And their websites link to regional tools, data, and other educational materials. A particularly useful tool is the Climate Hub's Toolshed, which is a database of tools that are relevant to climate variability and change, as well as other factors such as drought, pests, and extreme weather. I mentioned the NOAA RISA. So the NOAA RISA teams work in sustained partnership with local decision makers to help stakeholders understand and adapt to regional climate impacts. And so the types of products and management efforts undertaken by the RiversEdge vary widely, but they share the common feature of emerging from real-world challenges faced by stakeholders. The RiversEdge teams that serve the Southwest are the California Nevada Applications Program, or CNAP, the Climate Assessment for the Southwest, or CLIMAS, the Southern Climate Impacts Program, or SCIP, and the Western Water Assessment. You can tell how much climate service providers like our acronyms. So some of the services that they provide include various tools, seasonal predictions and outlooks, and climate data. And one example is the Intermountain West Climate Dashboard that provides seasonal outlooks and temperature, seasonal outlooks of temperature, precipitation, and snowpack for Western states, drought monitoring, current and forecasted stream flow, and also reservoir storage data. The tree flow database is another example, and this database provides stream flow reconstructions, data access, and examples of the ways in which water managers are using stream flow reconstructions. And then lastly, I just wanted to mention that CLIMAS provides a monthly climate outlook for their region, which is Arizona and New Mexico. And this outlook recaps weather over the past few months and also shows the outlook for the upcoming months. So those are just like some examples of what the NOAA RiversEdge provide. And then lots of federal government agencies, in addition to hosting climate service organizations like the ones I've just described, they also provide other resources on climate change. So example, the USGS has a national climate change viewer that displays climate projections for various parameters, including temperature, precipitation, and runoff over the next 100 years, viewed by state or watershed. Users can choose the time period they're interested in and which model and future scenario they would like to view. So if you go to the website right now, it explains that they're currently working on a revision of this viewer, but it should be coming out soon. The Bureau of Reclamation has a climate change page with risk assessments and other reports, a WaterSmart page with basin studies and river basin assessments, and a tool that provides data and maps for viewing climate and hydrology projections in U.S. river basins. And there are also several nonprofit organizations that provide tools and resources related to climate information. And perhaps the most well-known is the Climate Adaptation Knowledge Exchange, or CAKE, which is founded and managed by EcoAdapt. The interactive online database, it provides information via a virtual library, directory of practitioners to share knowledge and data tools and information from other sites. And then another nonprofit I wanted to mention is the Conservation Biology Institute, which, among other things, they provide a mapping and analysis platform called DataBasin that allows users to explore over 2,000 data sets, create custom visualizations, and publish data sets and maps. And then lastly, I just wanted to talk about the universities and state climate offices. So universities are often a trusted source of climate information as well. They may host useful tools, such as this one here, Drought View by the University of Arizona. And Drought View allows the user to visualize drought parameters, including vegetation and precipitation indices. And then another example is this digital climate atlas for Mexico. And this is from the National Autonomous University of Mexico, and it allows visualization of past and future climate data for the country. And so the researchers at universities themselves are also a great resource too, as they're often willing to collaborate with practitioners on issues of mutual interest. And then state climate offices. So there's a state climate office in each state, with a state climatologist appointed by the state to be a source of statewide climate information to support researchers, stakeholders, and the general public. And so the climate office is usually based at a local university. State climatologists work closely with other climate service organizations. They regularly give presentations and respond to inquiries. And then the State Climate Office websites also provide weather and climate information and links to other resources, including climate data and seasonal outlooks. Okay, so I just went through a whole bunch of climate service providers. And of course, you guys remember all of the ones I just mentioned, right? Just kidding. So luckily, some other people recognized how many climate service providers there are. So the organizations that I've listed here, they realized that there are so many climate service providers out there. It was really getting hard to keep track of them all. And, you know, how is someone supposed to be able to find the provider that will help them get the information that they need? And so these organizations created a database to make it easy to find service providers. So the user can search by state, sector, timescale, types of service provided, and other parameters to figure out which provider they should contact for help. So this, you know, this would be a good first place to go when you're starting out looking for help. So I wanted to mention a couple other tools. I mentioned some already, but I would be remiss if I didn't mention a couple more. So the U.S. Climate Resilience Toolkit, it's really a one-stop shop for climate adaptation tools, case studies of climate resilience, reports and state climate summaries, training courses, and help in finding service providers as well. And probably the most popular tool it provides is the Climate Explorer, which allows the user to graph and map historical and projected climate data for any county in the US. And then another tool worth mentioning is the Climate Toolbox, which again houses many tools helpful for planning for climate change impacts. And so there are tools for mapping historical and future climate, graphing future stream flow, mapping future hardiness and crop suitability zones, and also graphing seasonal forecasts for a given location, plus many more. And then lastly, I just wanted to mention assessment. So in addition to all of the climate services available, there are also a myriad of climate assessments that can prove useful in planning by providing past, present, and future climate information for your region of interest. So there are national assessments, such as the U.S. National Climate Assessment that's updated every 4 years, and many other countries have their own national assessment reports as well. There are regional assessments, such as the Assessment of Climate Change in the Southwest U.S., published in 2013, and a global assessment run by the Intergovernmental Panel on Climate Change, or the IPCC, which is updated every 7 years. And so the next IPCC report, the 6th assessment report, will be published later this year. So trying to tie this all together, I wanted to take a quick look back at the Escalante River example that we were introduced to earlier this afternoon. So using some of the services and the tools that I've mentioned, in this presentation, I've gathered some weather and climate information that might be useful in adapting this project in anticipation of future climate change. So using the Climate Explorer tool, I've mapped here temperature from 2017 to present, and also precipitation over the same time period. And this is from the Grand Staircase Escalante National Monument Weather Station. And then next, using pretty much the same variables looking to the future. So I used Climate Explorer again. And so the top graph shows the projected average daily max temperature. And then the bottom graph shows the projected total precipitation. And these are for Kane County, Utah through 2050. And so it looks like precipitation is unlikely to change much. And this is common throughout the Southwest for the future, but max temperature will likely increase by about 4 degrees Fahrenheit by 2050. And so the temperature alone will increase evapotranspiration and dry out soils, even if there's little to no change in precipitation. So next I wanted to look at stream flow. And so I used the tree flow tool to plot this is the 10-year running mean of reconstructed Colorado River flow. This is at Lee's Ferry from the years 1490 to 1997. And so the reconstructed values here are shown in blue, in this graph, and observed values are shown in gray. And the long-term reconstructed mean is that dashed gray line across the middle. And so this data can give us an idea of what stream flow has looked like in the past at this site at Lee's Ferry. And then taking it to look to the future for stream flow, I used the Climate Toolbox tool to plot projected stream flow at Lee's Ferry, so the same site, for the years 2040 to 2069. And so the black line here shows the historical values, and then the orange and the blue lines show two different future scenarios. And so we can see that the peak in stream flow is projected to occur about 1 month earlier, now in April to May instead of the June to July range. And this is based on either future scenario. And then percentage-wise, breaking this up by percent, this means that we could expect much higher than normal stream flow in April compared to historical records, but much lower than normal stream flow during the summer months. So wrapping this all up, some big takeaways. So as you can see, there are tens, if not hundreds of tools, assessments, and other climate services that are available to help practitioners when planning for climate change. Climate service organizations are a great resource to turn to, and they offer many different resources, including funding opportunities and expertise. And really don't be afraid to reach out. It's our job as climate service providers to really help in any way that we can. So thank you.
Thank you, Sarah, for your presentation. Really, there's a lot of information there.
Yes, there is.
And again, what's that?
I just was agreeing with you. Yes.
Yeah, I mean, it's one of the challenges that you and I and other authors of the guidebook, one of the challenges that we found is just how much climate information is out there, which is a great thing, but it is super challenging. We will entertain questions to you from the audience until, why don't we just for another couple minutes, I guess, and then we'll probably just open it up, Sarah, if that's okay with you, to the rest of the presenters and have a little more of a freewheeling discussion. But please, if you have any questions specific for Sarah, please type them into the chat box. Sarah, I had a question for you, maybe just kind of more related to your work with the U of A, et cetera. I know there's probably no typical day for you, but how do you generally interact? How do you get on the radar screen of the public? And I'm, kind of thinking of the Escalante case study, someone in Escalante that wants to reach out. It may not be to the U of A because they're in Utah, but how does that connection usually happen with the public, like for presentations and information gathering, that kind of thing?
Yeah, so I mean, we have a lot of outreach that we do. And actually most of these climate service providers that I mentioned all do some sort of outreach via presentations, webinars. We actually have a podcast now too. But really, like I said at the end of my presentation, don't be afraid to reach out to us. And I think that climate services database I mentioned is a great first stop. So say you're in Utah, you can go on there, you can search for Utah service providers, you could search for the types of information you're looking for, and then it'll pop up all of those service providers. You can go to their website, and then, like my contact information is on our Southwest Cask site. And so it's an easy place to just reach out via email usually for the information that you need. I'd like to also add that most of these providers provide funding opportunities as well. And so I'll put a plug out. We have a funding opportunity that just came out last week, and I'll put the information into the chat box. But one of the research priorities specifically says climate-informed management of natural resources in coastal, freshwater, and riparian ecosystems to support effective climate adaptation.
Mhm.
So a little caveat is that to be a PI on one of these projects, you have to work at one of our consortium institutions or for the USGS, but you can always partner with those researchers, right? So if you're a manager and you have a project, you want to find out more climate information for your site, you can reach out to researchers at these institutions and ask about partnering. I mean, researchers are always looking for cool new projects and partnerships. So I'll pop that in the chat. We also, for the students on here, we have a fellowship that's out right now too. So I will also put that link in there. And yeah.
Thank you, Sarah, for mentioning that. That's great. And there was actually, no, I'm sorry, it was Liz made a comment kind of along the lines of what you and I just talked about, is the amount of resources. And she said she was furiously taking notes.
Yeah.
And is there a list? I mean, we of some of the resources that you gave in your presentation. I mean, your presentation will be made available, but Liz was just trying to get, sort of a ready available
Right.
list of that information.
Not that I know, obviously the guidebook, but if you don't want to pay for the whole thing to get, the list that we have in there. Again, I think that climate services database is a good place because that has everything, but I don't know of a just list. And that's why those people I would helped out on that as well, but that's why that database came into existence, is for that reason, right? There are so many, and I mentioned it's really skyrocketed over the past decade or so, the number of providers. And so that's a good first place to start.
Well, great. And put, if you can, Sarah, put the link of that database in the chat box too. I mean, that's a great, at least that's a good initial beginning to get us.
Yeah, it looks like Ashley wants the podcast too, so I'll put that in there. And I will mention, this goes from one of the earlier questions about lessons learned and leaving water in streams for restoration purposes. So the Santa Cruz River, Mark knows this, in Tucson water had extra reclaimed water. And so they started putting it into the Santa Cruz River, which was a dry riverbed due to Tucson, essentially. And so there was a great research opportunity there for restoration, right? And to see the river come back. And we did a podcast episode where we talked to Tucson Water and local researchers about that project. So we try to do some lessons learned type things on our podcast as well.
Great, Sarah. Thank you for that. Let's open it up. Back to Michael Scott, Bart Wickl, Catherine Higo. If Catherine was able to join us, please go ahead and include some additional questions in the chat box. Let's see, we got the links there. Catherine, are you with us? Because there is a question for you in the chat box that I can send out, or maybe send out to everybody. Catherine maybe was unable to join us again, but I have a question circling back to Michael Scott. Put you on a hot seat, Michael. Well, not much, really. Michael, from the presentations, do you, and sort of thinking about the Escalante's restoration work in particular, what do you think, and looking ahead with your knowledge of the Escalante Partnership's restoration actions on the river, anything kind of jump out at you as to what might be a viable tact from a climate adaptation perspective? I'm thinking kind of in particular, like, maybe potentially changing their restoration vision or objectives a little bit based more on climate knowledge, maybe even specific locations of where they're focusing some of their restoration work, maybe the restoration tactics themselves along those lines. Or maybe they stay the same.
Yeah, I mean, I guess some of the concepts of, looking at, to me, I was just thinking about some of the ideas about the state changes. It's kind of why I wanted to bring in the idea of the fact that the Arroyo cycle is just such an important part of the history of the Escalante. And that that Arroyo cut-fill cycle really was very much driven by climate and controlled some fairly dramatic differences in ecological states over time. And so thinking about that in terms of future climate and say more intense large floods, which historically over the last several thousand years, those are what sort of drove the Arroyo cutting and widening. And so one sort of question I had in the context of climate change going forward is, I mean, historically, the valleys would fill over hundreds and even 1,000 years during periods where the climate was slightly wetter and cooler, and there was less frequent and intense large floods. And then the Arroyo cutting and widening part of the cycle occurred during drier times with more intense large flood events. So going forward, I mean, in a drier climate, are we potentially stuck sort of more in this sort of the Arroyo phase of the of the Escalante, in which case, are we looking at just more flooding, more evacuation of sediments? And then you have to start thinking about, well, what does that mean in terms of the state of the riparian and riverine ecosystem? That's very different than what it would be, say, during a cooler and wetter climate phase. So, in that case, I would think that you would certainly be looking at a much sparser riparian corridor, and that you would be really pretty limited, I think, in terms of what sort of options you might have in terms of maintaining, certainly maintaining the cover and extent of riparian vegetation you have there now would be pretty unlikely. So,
Great.
Yeah, I mean, I don't know if I really answered your question there, but just some of the previous presentations just sort of got me thinking in terms of, this idea of, well, how do we adapt, the systems that we have to future conditions, which I think are likely to be really quite different.
No, you did answer it, Michael. I put you on the spot. I mean, it's a difficult question to answer directly. I had a follow-up question, but also, again, want to reach out to the audience because I'm not getting a lot in the chat box here. But before I answer my follow-up question to, I guess, to you, Michael, but also to Bart and Sarah, I don't think Catherine was able to join us. I want to ask Sarah and Bart if you all had questions for the audience or other presenters. Don't want to leave you out. Don't want to let you guys just sit there. And while you're thinking of it, someone just saved you. I got a question from Carrie. The question is, are there any political entities in the U.S., like state, county, that recognize ecological flows as a beneficial use of river water? What has been the experience of other countries that recognize the right of rivers, like Australia and Africa, Colombia, etc.? Anybody want to take that?
Sure, I'll bite.
Yeah, I think it's interesting. The field of environmental flows is fascinating because it was born out of necessity. The first thinking about over-allocation emerged actually, I think, in England in the early 1900s when we over-allocated so much water and realized that the sewage wouldn't flow anymore. And we're like, oh, we got to keep some flows in this river to actually get the wastewater out. I think in South Africa, Australia, and other places, Mexico, the initial building of the concept of environmental flows is also built on scarcity, or in the US. And I think what you see now as an opportunity is expanding the concept of environmental flows to watersheds where there isn't a scarcity problem yet, but as a preemptive tool in adapting to climate change, making clear that with greater variability, we have much less flexibility in our allocation of water. And I think that is a big one. In California, there's a big example now with our drought over the past decade, or extended drought in the past couple of years, where we clearly see that the saltwater intrusion that's coming up the delta is really causing major problems and actually could cut off the whole northern water system in California from the southern. So the water transfer that's currently taking place, you may have heard of the tunnels that Jerry Brown was proposing and as a solution. And that was sort of, in their mind, a climate adaptive solution for the eventual infiltration of saltwater. Environmental flows obviously have an important role. And if we had a bit more of a broader vision, you could make a strong case to leave more flows in the system, which would be cheaper than building very expensive tunnels and vulnerable tunnels. So anyway, there's some examples there, absolutely.
That's great, Bart. I want to acknowledge a couple things. One, it's 3 o'clock, and so, but I don't want to cut us off here. I would like this conversation to go on, at least with regard to this question, because it's an interesting question that we were discussing. So maybe if you all can stay for a few more minutes, it looks like a lot of our audience can as well. So maybe just stay on for a while. Catherine Higo has been able to join us again. So hi, Catherine. And so just to kind of close this out in quotes, just want to say to the audience and to our presenters, everybody, thank you so much for joining us. This has been great panel. A lot of excellent information. Really appreciate everybody time and effort that you all put into doing their recordings. I got away without doing one, which was kind of mischievous on my part, but I appreciate the challenge that sometimes it takes to do those pre-recordings, because you don't have the energy of the audience in front of you, and that is challenging. So for folks who can't stay with us for a few more minutes, please, again, we're going to start tomorrow, same time, probably the same place. And go ahead and look at our agenda, which is online. Just Google RiversEdge West Conference 2021, get at our agenda, and you'll see the entire agenda right there. And so thanks again. And we'll just continue maybe with this question and maybe one or two others just for a few more minutes this here while we're here right now. So the question, Catherine, right before, because I want to kind of continue with this, because it's I think a really interesting question that we were discussing when you popped in, Catherine, was, are there any political entities in the US that recognize e-flows, essentially ecologic flows, and maybe other countries as well? And Bart was discussing that, and from my experience, I think the short answer is no. But there's a big but there. But go ahead and if you have a response to that, Catherine, and otherwise I certainly do.
Well, I do know, for example, during the 2011-2012 drought in Texas, that there was a lot of debate between the amount of water that went to the rice farmers downstream, that went to maintaining ecological flows, because you need a certain amount of fresh water going into Galveston Bay, And of course, supplying everybody who extracted water from those resources, because a lot of Texas is surface water driven. Some is aquifer, but a lot is surface. So that was part of the mix. But in terms of actual requirements, I am definitely not the person to ask about that.
Yeah. And in my experience, I mean, again, the short answer that I've seen in my work is no. But that said, I feel like, and in Bart's presentation, we discussed this a little bit, is that there are some great examples on a really small scale where e-flows are not recognized per se, but there's been some innovative progress in water management. And I think, again, per what Bart, I think specifically was saying in his adaptation presentation, is getting these scarce drops of water devoted to either legally, politically, or both to e-flows, I think is a really steep climb. But there may be mutual benefits in changing water management that would benefit native species and people. And I think this is being done maybe haphazardly and maybe without even with the objective of benefiting native species, but it's being done at least with progressive water management on a small scale, and amplifying from that may be something to look into.
Mark, I'd like to add one thing here. In the US, no, you're right. I think the reality in water management in the US is this incredible fragmentation, and especially our work on the Rio Grande has made that very clear. When you go to Mexico, there's, for better or for worse, CONAGUA, one water agency that manages all water in that country and has this top-down, incredibly bureaucratic system to manage water. But at the same time, they were able to launch a national environmental flows program. Now, what that means in reality remains to be seen. In other places, Australia, you got the Murray-Darling Basin Authority, you got a national environmental flows program in South Africa. And so other places do have experience with that. And typically, a key ingredient seems to be having a somewhat more centralized government, and then also a specific entity, a basin, river basin management entity. And actually, that might be a key ingredient also for greater adaptation success. In Europe, water is managed through the European Water Framework Directive, which is an adaptive water management framework. It's a really interesting contrast with US litigation, where once things are put down on paper, you don't want to touch it again, because the moment you open it up, you're doomed. I think the Endangered Species Act is a beautiful example of that. The moment you open it up, who knows what's going to come out. And to just point towards Europe as an example, at least there's sort of a 5-year cycle of adaptive adjustment of these policies. Now, if that's resulting in a much better situation, I don't know. I'd like to think so. I do see that the Endangered Species Act is a highly unadaptive, a non-adaptive or maladaptive kind of piece of litigation, legislation, whatever. Yeah.
Sorry, were you going to continue, Bart? I interrupted you.
No, that was it. Sorry.
Okay. I was just going to say, you touched on something that was really interesting. When you start looking globally at this issue, is like, for example, you touched on Mexico, is the difference between Mexican water management and US water management is huge. I mean, US water management is bottom up. I mean, it's very locally driven, whereas water management in in Mexico is, like you said, completely top down. And so when you have like a binational river like the Colorado or Rio Grande, it's a real interesting juxtaposition of perspectives when it comes to river management.
In China, you've got a very centralized water management, but it's definitely not working better. And then India as an example, you can also have places where there's just a much greater cultural value of water, spiritual, religious value that is in the Ganga River. And so it's very much context specific, and yeah, as always with water.
The other thing I wanted to mention before we leave this question, unless there's you all have additional comments, is in terms of other nations looking at flows, ecologic flows, is the Murray-Darling Basin, Australia. There's a lot of lessons there. It certainly hasn't functioned perfectly by any stretch of the imagination, but there's a lot of great lessons there that we in the US could potentially apply here. There is, we got one last question from the audience, and maybe I'll just ask that, and then maybe if you all have any last comments, words of wisdom, questions, and then we can close with any last thoughts. So the question from Jonathan is, to you, Bart. Bart mentioned near real-time monitoring as an adaptation, and he would like you to, if you could, expand on that.
Yeah, I think to reflect on the Colorado River example that I gave with the Hoover Dam, you can see that that piece of infrastructure is built with 20, 30 years of climate data. And actually, it seems that Michael Scott's first slide was taken exactly at that moment when it was nice and wet, and the Escalante was flowing quite a bit. I think understanding that much longer climate history is important, and then having much more near real-time monitoring with remote sensing kinds of approaches and other measurements to see where we're headed. How are we setting a target and seeing how we're meeting those targets over the years. And, if we set out to reduce Russian olive, and 10, 20 years into our program, we're actually still seeing an expansion, and clearly we're doing something wrong and we're not meeting our management targets. And I think with a 30, 40 year openly accessible satellite sequence of simpler, often regarded as not so interesting, but Landsat data, for example, you can really start establishing what has happened over the past 40 years and how can we track where we are now in comparison, at least to the past 40 years. And we can do that on a almost near real-time basis. Every time a Landsat image comes in, we can check in and say, hey, where are we? We see this with forest fire monitoring. We're getting much better tools. And so, yeah, I think we can really start employing those much more than ever before.
Thanks for that, Bart. And got a couple other comments here that rolled in while you were answering that question. Ben responded to our previous discussion on water rights and e-flows. He says that the state of Washington has at least stated that there's a state law requires that enough water is kept in streams and rivers to protect and preserve in-stream resources and values of fish, etc. Navigation, one of the most effective tools for protecting stream flows is to set in-stream flows, which are flow levels adapted into rule. And there was a great comment from Ashley, which I was thinking the same thing. She said, interesting, Ben, Washington has a lot of water. And yeah, I mean, and it kind of brings us back to kind of something that we touched on earlier is it would be great. I mean, Washington and other states as well, where there might be laws in place, but just to see what kind of examples are on the ground where if there is a law, has e-flow actually been implemented? And if so, what has been learned in the process that could be provided for benefit of other efforts elsewhere?
Mark, there was a question earlier for Catherine also. And actually, I think the rest of us. But
do you see it right there, Sarah? Go ahead and read it if you got it.
Do you still feel the carbon fee and dividend system proposed by Citizens Climate Lobby is still a viable program to implement at the federal level? And then also any feel for how organized and how aligned key players are in the new administration in addressing climate change actions. I could speak to that one, but you go first, Catherine.
Yes, you can probably speak to the second better than I could. I would ask why the straw man? Why still viable? What would make it not still viable? I'm Canadian. There's a price on carbon in Canada. They just ratcheted up. It's going up $10 a year till next year, and then it's going up $15 a year after that till it reaches $130 a ton Canadian, which is about $100 a ton American, which is what it needs to be to actually reach our Paris targets. There are, I think, at the last count, something like 64 countries around the world that have some type of price on carbon. And the US already effectively operates with a low price on carbon because of the various forms of legislation that are already in place, as well as hefty fossil fuel subsidies. Let's not forget that. Fossil fuel subsidies currently amount to more than the Department of Defense's budget on an annual basis. So I don't know why still viable would be the question, because it's been viable. It's been proposed for 100 years. That's how long this thing has been proposed, the idea of a tax on externalities. And now I would say it's more viable than ever because it's being put in place in other trading markets that would allow the US to equalize its economy with those markets. But in terms of how the new administration is addressing it, it's not front and center in their current efforts. And maybe you could comment more on that, Sarah.
I can't necessarily comment to the carbon fee piece of it, but I can say that the new administration, I mean, climate change seems to be pretty high on their priority list. And I know, since we're a partnership with the USGS, the past 4 years we've struggled with the previous administration and worried about funding regularly, and had to watch what we say in certain instances. But now we're full steam ahead, lots of support from the administration, DOI. I mean, how awesome is it that the new director for the DOI is Native American from New Mexico? I mean, that's like, wow. So I think in terms of climate change in general, we're really excited for the new administration. I can't speak to the carbon fee piece of it, but the rest we're excited about. I have a quick question for Catherine. How do you do that with your presentation where you it's your video and then your slides? I don't, is there a trick?
It was really cool.
Right? I don't know how to do that.
The trick is called iMovie. And it takes a little while, but I taught it to myself, and it's not super hard because it's drag and drop. So you shoot your video separately, and then you turn your slides into JPEGs, which you can do from PowerPoint. You just extract as JPEGs, and then you put them all into iMovie together, and you've got your video track here, and then you just pull down the PowerPoint slides whenever you want them to appear.
That's pretty cool.
That's it. I highly recommend it.
We got to do a workshop on that, Catherine. Sarah, going back to that comment you had, and then we'll close this out, but have you got any inkling from the new administration? I get the whole change in perspective, and it is a wow moment. Couldn't be even more dramatic, but any inkling on funding for some of the programs that have been so underfunded during the last administration?
I mean, I'm not really, high up there. So I don't. My inkling is that, hopefully we'll see more funding for sure. But you know what? We at the Climate Adaptation Science Centers, we actually saw more funding during the previous administration, surprisingly. So, I mean, Congress seemed to be pretty supportive still, even in the past administration. So, I mean, we're hopeful. I mean, we have an RFP out that came out last week, and that hadn't happened in years. So I think that we are seeing more funding already. That's just in our center, but yeah, I would say it's positive.
Okay, keep up the positive thinking. Yeah. Barton, you had a comment, but just want to, in the name of closing this out, again, personally, I want to thank all of you for joining us and taking the time. This has been wonderful. And if you have any closing thoughts, comments, resources, anything you want to put in the chat box to leave us, please go and do that. Bart, you had a comment. You might as well just go ahead and read that off. And Michael, Sarah, and Catherine, if you have any last thoughts, please chime in.
I do. So first of all, sorry, just with the video, Rob said that the slides weren't up quite long enough, but the whole point of the video is it's recorded. So you can go back, you can hit pause, and you can sit there as long as you want. That's the point with the video. So are you posting, did you already say, Mark, are these going to be posted online, or how are you making the videos available?
Yeah, well, they'll be posted online.
Okay, so don't worry, Rob, if your notes are incomplete, you go back, you just hit pause, and you can stare at things for as long as you want. But I would love to speak to the final question that here we go, that Sarah Marshall had, and Sarah's already been answering this a bit in the chat too. I think this is a great way to end. As scientists and communicators, what gives you the greatest hope? And she says, you know, specifically for river ecosystems in the Southwest US, but frankly, I think you could apply that to anywhere. And here's the interesting thing. About 3 years ago, I started to notice that wherever I go, I was getting this question from everybody, everywhere, any age, any demographic. I was getting this question, what gives you hope? So I decided to turn this around, because when I give longer presentations, I use polling software where I can collect answers from people. So I collected hundreds of answers from people. I asked them, what gives you hope? And then I analyzed them, and being a scientist. And this is what I found. I found the number one thing that gives us hope, and the social science backs this up, is recognizing and seeing other people acting. So when we realize that we are not alone, that there's a whole bunch of other people out there that care, that this issue isn't a giant boulder sitting at the bottom of the hill and there's only like 10 hands trying to roll it up. No, there's lots of hands, and the boulder's already at the top, and it's actually rolling slowly in the right direction. That is what gives us hope. And the idea that there's something to leave for the next generation. It's not that we hope the next generation is going to save us. It's that there is a next generation to leave this to. The land that we love, the places that we love, this incredible planet that's our home. So that's really what it's about. And so although the science explains what's happening, connecting with each other over what people are doing is so important. And that's really, I think, what gives us hope. And Sarah, do you want to share what you said too? Because I think that was really helpful as well.
Yeah, well, I fit in your number one category, because I said what gives me hope is all of you, you know, working to adapt streams to climate change, right? I mean, that's what a lot of what this conference is about, and a lot of, you know, all of the partners we work with, like they care, they acknowledge that this is happening and we need to adapt to it. So all of those partnerships, all the people we work with, they're what gives me hope. So I fit your number one. We're not in this. We're doing things.
I think one of the things that gives me hope, specifically to river systems, that I've found after years of working in some of the most hammered river systems I've ever seen, is their ability to come back. They are so resilient. So if you can do some things on the ground or policy-wise to change water management, whatever it is, with dams, with cattle, with urbanized areas, you can release some of the minimize some of those impacts. Rivers can and do come back, and they can come back quite quickly. And so that, to me, is some good hope. Sometimes it's not as bad as it seems.
Got a visitor.
And Catherine, thanks for highlighting Sarah's question. I saw that earlier. Got a little bit buried. Michael, Bart, any last thoughts? Words of wisdom? We've tapped you guys quite a bit, so don't worry if you're.
I like your point, Mark. I think that's probably one of the strongest ones, where especially freshwater ecosystems or river systems are built through a disruptive regime, and yeah, I have hope that they're able to make it through a lot longer. So I think that's a very good point. And you see that with the example from Washington that was brought up. The Klamath is already coming back with a vengeance, and that's really cool to see. You take one dam out, and there's this incredible ecological recovery taking place.
Well, that's like that Santa Cruz River example I mentioned earlier, right? That riverbed was dry, and within a year, were already seeing species that were there, 100 years ago.
A little water, little nutrients.
Yep, it's the kids too, right? Kids are resilient. That's what my daughter with COVID has been very resilient, so she gives me hope as well.
Well, thank you all again. Michael, Sarah, Bart, Catherine, really appreciate you guys. Presentations, taking the time and everything. It's been wonderful to see your faces. Next year, maybe we can do this in person. Let's not wait a year. And for those still in the audience, thank you so much for joining us. And please come back tomorrow. We're starting the same time. And look forward to hearing from you and seeing your faces then. But in the meantime, thanks again, you all. Appreciate it.
Great.
Thank you so much.